And you can calculate now to a precision of better than a percent the spectrum of all those particles that were being discovered at Berkeley. This was my dream.
Hi, and welcome to the Origins Podcast with Lawrence Krauss. This week, I had a discussion with the theoretical physicist David Krauss, who won the Nobel Prize in 2004 for his contributions to understanding one of the four fundamental forces in nature, the strong force, which set the basis and really completed the description of the standard model of particle physics, a model that's so good, a fundamental theory that's so good that not only can we use it to calculate certain processes to 14 decimal places of accuracy and compare them to experiment, but it's also withstood the test of time. For over 50 years, every single observation at the fundamental scales has been in accord with that theory. David is one of the preeminent theoretical physicists who's been involved not just in the development of the theory of the strong interaction called quantum chromodynamics, for which he won the Nobel Prize, but also he's one of the founders and developers of what's called string theory, and we talk about that as well. Our discussion spanned physics from the 1950s to today, and David has a unique knowledge, not just of theoretical physics, but of the history of physics as well, having experienced an incredible series of episodes, and we talked about those and his interaction with some other well-known physicists. It was a fascinating discussion, again, I think unique in illuminating aspects of the process of scientific discovery and potentially the future of science as well. I hope you'll enjoy the discussion as much as I did. With no further ado, here's David Krauss. Well, thank you very much, David, for allowing me to virtually be with you in your study and have a conversation. It's great to talk to you.
It's nice to see you. We saw each other a few weeks ago.
In reality, yes, and we've both been vaccinated. So even here over Zoom, we can be safe. And it's nice to be vaccinated, and it's nice to see you doing so well. And it was fun to see in Santa Barbara. I want this dialogue to be kind of wide ranging about probing many aspects of your many intellectual endeavors and ideas but since it is the Origins podcast, I want to usually begin. We like to begin with your origins. So I want to talk a little bit about what got you into science. You grew up in DC. You were born in DC, and did you grow up there?
I grew up in a suburb in Arlington, Virginia.
Arlington. Were your parents work for the government, or?
My father worked for a variety of government agencies and the Senate staff and Council of Economic Advisors.
Was he an economist?
He was a self-taught economist. He was an English major.
The best kind, I guess, or I know we both have views about economics that are similar. It's not particularly complimentary in general, but so where they both so was he was self-taught. He wasn't an academic in any sense then. He didn't have an advanced degree or anything.
No, he had a master's in English from Penn, and he, I think, really would have liked to have been a playwright if he had been able.
There's not a lot of easy work in that field. It's harder than being a physicist. What about your mother? Was she
a remarkable woman, born in the Ukraine, survived the war, the Civil War, the pogroms, and came to this country at the age of 6. And graduated with a degree in chemistry from Barnard.
Wow. So she was a scientist.
Well, actually, she was a housewife at the end.
Yeah, but she had scientific sensibilities, maybe. Let me put it that way.
Yeah, she definitely was interested in science. And
well, okay. Well, you know where I'm heading, which is where did your interest in science grow? Was it there as a young person, or did it develop later on?
It developed rather early. His family was very intellectual, and but the dinner conversation, which was fierce, was mostly concentrated on politics and on events of the day. As my father's career and interests dominated.
Mm-hmm. Not unusual.
But there wasn't much science or interest in science at home, and I think I got really interested in science when I was in Israel, which we moved to when I was 12.
Ah, I didn't know that. I was going to ask why on earth, if you grew up in DC, did you go to university in Israel? But okay, well, you skipped that part. You moved to the whole family moved to Israel. Okay, interesting.
My father, in a sense, was a refugee from the Eisenhower administration. So he had worked in democratic administrations in various capacities for all of his life. And when the Republican Revolution of '52 took place, after 20 years of democratic rule, at that time there were no places like the Heritage Foundation or things, Brookings, and places which, and since he'd never got a formal doctorate in the areas in which he taught himself, political science and economics and stuff, he needed a job, and he got a bunch of jobs sort of advising foreign governments. He went to Korea, actually, in '52 or so to give advice to the struggling Korean government.
That was just him. The family didn't go, right? You didn't move there. Yeah.
But later he was invited to join a rather distinguished group of ex-democratic people out of a job to be the first U.S. delegation to Israel, which came along with the first U.S. foreign aid to Israel.
Oh.
And the American government said, well, they'll give you a lot of money, but since you obviously don't know how to spend it, we'll send experts to teach you how to spend it, since we have a lot of experience with a young country who's doubled its population from refugee camps in Europe and has just fought a war with the Arabs, and it's just beginning. We can tell you what to do.
This was 52. So this was the first U.S. foreign aid. I mean, Israel was 40. Wasn't Israel 48 or no?
Israel began in 48, but the U.S. was torn between oil and Jews.
Still is. Okay.
Anyway, so we went to Israel, got on a boat in those days, and
wow,
and moved the 4 boys.
Wow.
Israel, which was just beginning, very poor, still rationing, food rationing. We were kind of, since we had some kind of diplomatic status, in a rather rich position, but I was sort of thrown into school with almost no Hebrew. And, in Israel at that time, Jerusalem, where we lived, the seat of the government, was a small town of 50,000 people, half of them crazy, but enormously interesting people from all over.
Yeah, I can imagine.
So it was very, very exciting. And my father was an advisor to various ministries in the government, was in the middle of it all. So it was an exciting time. But there was, there was like one movie theater in town, no television, no nothing. So I really became an avid reader, and I got hooked onto science by actually reading popular science books. Speaking as I am to a popular science writer.
Well, no, same for me, and that's one of the reasons I write in return favor, because it was everyone from Einstein and Asimov and Gamow and even James Jeans. But what about who turned you on?
Einstein and George Gamov's books and Eddington and anything I could get my hand on, which wasn't easy since it was much harder then to get on, especially all the books in in a place like Israel. But
Yeah.
I got a book, which I still keep close by. Here it is. It's for my bar mitzvah, which was in Israel. It was called The Evolution of Physics.
By Einstein and Infeld. Yeah, famous book.
And the great thing about this was I was given this book by Leopold's brother, Heinrich.
Oh, wow.
As a bar mitzvah present. And it was signed, as you can see,
Yeah, okay, signed, yes.
by Albert Einstein.
Wow, really? That's a real signature.
Yeah.
Wow.
The only second time I saw a real signature of this was when you go to the Nobel Prize Foundation at the end of the week to pick up the check, you have to sign the book.
Ah.
And exactly the same signature.
Yeah, no, it's I've seen the signature. I have copies of it because when I was chairman of the physics department at Case Western, where Michelson had done, it wasn't that Einstein corresponded with Michelson, but he corresponded with a nutty chair later on who spent 40 years trying to disprove relativity and had come up with some, and Einstein corresponded with him about what was probably wrong with his experiment. So I have copies of those letters with his signatures, but that's good. That book, well, guard that book. It's worth something.
It was worth more to me. So that really turned me on, I think.
Was that the first? I mean, I was wondering what the first book for me, it was a book about Galileo when I was 11 or 12 or something, but was that the book that really got you going?
Yeah, I don't know. There were a bunch of books. I still have a bunch of them. 1, 2, 3, Infinity.
Yeah.
I
love that book. Well, now, but did your parents, so it was bar mitzvah present. Your parents, didn't sort of encourage or like give you some science books early on or anything like that? It was just it was basically that and your own personal, was it teachers? Any teachers turn you on?
No, it really was the books. And it was not just books the books about science, but it was really the books about theoretical physics. So
yeah, okay. Then you knew right away. You enjoyed. Before we get to that, so were your parents obviously were interested in Israel? They were, some of them had been, immigrants who had been saved, Jewish immigrants who'd been saved. But were they secular? Were they religious? No. They were just secular Jews but they obviously wanted to be there to support the formation of Israel.
Yeah. First, but also to get out of the U.S.
I can relate. I'm about to emigrate myself, so.
Adventure. Really.
Yeah, it was an adventure. Exactly. It must have been an incredible adventure for you, 12 or 13. At the same time, terrifying. As you point out, you didn't speak much Hebrew. And it must have been a little.
But it was enormously exciting because everything was new, and my father would travel around the country and take me with him often. So it was very, very, very exciting and interesting, although very different than sort of suburban America.
Yeah, absolutely. Well, that's probably why it was interesting and exciting. Yeah, absolutely. So it was the theoretical physics that turned you on. You knew that right away. It was something about and maybe because of
math, and I loved doing math problems. And I had a neighbor who, in school, again, it was too easy to get beyond the teachers. We would have an ongoing competition with doing integrals, which at that time was tough.
Yeah. No, that's great. Well, I was wondering. So you knew you enjoyed math. You had a math aptitude, but again, it wasn't school. It was pure. I had a few friends who were really good mathematicians. We never really. I wish, in retrospect, we'd spent more time outside of school, pushing beyond the boundaries of school. We instead just enjoyed, getting 100% and chatting, and but never really. There were some math competitions, but yeah, I wish it was great that you had, doing integrals. That would be neat. Yeah. And is that friend, by the way, did that friend become a mathematician or a scientist or anything? Do you know?
I think I lost track of him at some stage.
Okay. Okay.
Yeah.
But you chose to, but then you and your parents chose for you to go to Hebrew University in Jerusalem instead of coming to university in the United States. Was that again a
at a time? No, actually, I applied. They were. The U.S. was a long way away. I did apply to 3 universities: the University of Cambridge, Harvard, and some other place, and was rejected by all.
Okay, well, you shot high, but that's okay. You didn't have a safety school, except maybe Hebrew University. Was university free in Israel, or was it? It was what?
Essentially.
Yeah. Okay, like it was in Canada when I grew up. Okay, so.
It was a continental style university where you majored, and they, admitted a lot of students and then threw away 90%. It was one exam a year at the end. It was very much of a continental.
Now, and so was, okay, so that's when you really began to learn theoretical physics instead of math. And were there a lot of European emigre physicists teaching there, or what was it?
Head guy in Jerusalem at that time was Giulio Rocca of the Rocca coefficients.
Yeah.
Who was, one of the second generation of quantum mechanics scientists. He was a student of Fermi, and he taught quantum mechanics. And he was an excellent physicist, but there weren't many at that time in Israel. It was just beginning. I am kind of jealous of students who are beginning to study science or whatever they want at this point in the world, because it's so easy to get access to everything. It's such a gift.
Yeah, no, it really is. They definitely, when it comes to science, I guess there is some misinformation too, so you can get hooked in craziness. But yeah, being able to have access to so much, including, and that's one of the reasons why I do this too. But yeah, it is a very, the internet, for all its flaws, is an amazing resource for humanity, created, of course, by physicists. But anyway, or at least, created in its present form by physicists. But so were you aware of? So this was in the late 50s, early 60s. Then, is that right?
Was I aware of what was going on?
Yeah.
Vaguely, but not deeply. It was clear to me. So I was one of this kind of people who, very early on wanted to do theoretical physics at the frontiers of physics. And I was well aware that was in particle physics, but that hardly existed at all in Israel so directly. Again, only through reading Scientific American.
Okay, which used to be a good magazine.
Great magazine. Yeah.
It was a great magazine back then. And I used to write for it a lot. It's a great magazine back then. Now, you did a master's degree there too, or was that a pro forma thing like Cambridge? We just got that for being alive?
No, I didn't do a master's.
It says you do in your bio. I was just looking it up the other day.
Because you looked at Wikipedia, which is...
Yeah, well, it was the simplest thing to do. Okay, so I was surprised to see a master's degree. It wasn't something I would have expected you to do. But then I know in Cambridge, the way it works in Oxford, you get it automatically a year later just for being alive.
Sure. So as you know, masters, which have almost disappeared in the U.S. So at that time in Israel, that was the thing you did. You got a master's, and then you went. Some people went on to a PhD, but most didn't. But I was totally uninterested and wanted to get out of there and get to a real place.
Okay, well, that's the point. So you had a vague notion. You knew you wanted to do fundamental physics. You knew it was particle physics at that time. You knew enough to know it was particle physics. You didn't know about the brewing, all the stuff's going on. And then you chose what was really the center, in many ways, the center, experimentally at least, of particle physics. And what made you choose Berkeley?
Well, that time I knew well enough to apply to many places.
Yeah.
The only place that accepted me, I only again applied to a few: Princeton, Harvard, Berkeley, maybe Caltech. I don't know. I could figure out by then where the action was. But I was a nobody from. No, I don't think there had ever been anyone who had graduated with a bachelor's degree from Israel at that time who went on to study abroad. Those who did, they were just beginning. And those who did first got their masters, but I didn't want to get a master's.
Yeah, smart idea. Yeah.
So Berkeley was the only one who accepted me.
That's
Not from Harvard.
Well, I share that. Well, I grew up and I went to a small college in Canada and applied to, again, Harvard, Princeton, Caltech, Stanford, MIT. And I thought my safe school was Cornell, and I got accepted to MIT and nothing else. So that's why I went there. But it was.
I couldn't get people. I mean, to go to somebody like Rockout or one of my professors and get a letter of recommendation was almost impossible because nobody had ever done that.
Yeah. Oh, I see. Interesting. In my case, by the way, it was amusing. 3 of my professors went to Cornell, so that's why I figured for sure I would get into Cornell. But obviously, they didn't leave much of an imprint. Anyway,
was a lucky, because it really was the center of everything that was happening in every aspect of life at that time.
And in fact, I was just recently speaking to our mutual friend Barry Barish, who went to Berkeley a few years before you graduated in '62, I guess. And Berkeley, it was a great time experimentally in the sense that it was a great time, although it was beginning to get confused. There were particles being discovered up the wazoo. Every time you turned on an accelerator, many new particles were discovered, multiple resonances, and it was wonderful. But theoretically, it was beginning to get really weird and almost depressing. And so you came there and you, I don't know how long it took you to do your PhD. Must have come around 62 or 63 or something like that, or?
I came in 62 and finished my degree in 3 years, but stayed on for another year, sort of because my wife was finishing her.
Okay. Well, that's good.
But it was enormously exciting because in the realm of they were the highest energy machine in the world, 6G. My God.
Yeah.
At the Bevatron on the Hill, and they were discovering lots of hadronic resonances. So they were in the energy where you could, proton fixed target.
Yeah, it was fixed target.
You could produce particles, and so there would be lots of particles being discovered. And it was enormously exciting, and that totally turned me on to understand the strong interactions. It was,
which you eventually did, but it was a roundabout way. But well, actually, I think we'll get to that in a second.
I don't think anybody. It wasn't depressing. It was exciting.
Well, it was exciting, but let's. I mean, depressing in a sense that people were willing to throw out established theory. It wasn't depressing. It was some people were so confused that they said, "Well, our existing theory doesn't work. We'll throw it out." And
it wasn't. I look at it a little differently. There wasn't much existing theory. There was QED.
Yeah.
Great success of relativistic quantum mechanics. Feynman and Schwinger and Tomonaga and Dyson 10 years earlier. And, but that really hadn't changed anything. It wasn't anything new. It was just dealing with the rather technical difficulties of understanding relativistic quantum mechanics and understanding the so-called normalization, or sort of beginning of understanding.
Yeah.
The way that you could do calculations, and since it was such a simple theory, calculations worked, could be done very precisely and tested, and they worked beautifully. But then once you got into some real physics, with dynamics and zillions of new particles and resonances and clearly non-perturbative, can't be just understood as a simple corrections to a classical theory, which you understood very well. People were totally lost, and all attempts to mimic the same strategy as QED completely failed. So people were willing to try just about anything. Theorists, when presented with data that for which there's no explanation or prediction, will try anything, and everything was tried. But there was a a feeling that the golden path of just following the same path that led from Maxwell's theory to quantum electrodynamics wasn't going to work.
That was certainly the prevailing theory of you and your advisor, Jeffrey Chu.
Honestly attractive, so to a young student like me, I mean, my God, here you have all this data. It's quite complicated and rich, and there's some interesting patterns, but nobody understands really anything in a deep way, but lots of data. And Chu was one of those who said, okay, we need new ways looking at this which are divorced from what has failed. And what by and large, people who tried to do quantum field theories to mimic QE, quantum electrodynamics in the case of the strong interactions, failed so miserably that nobody was trying anymore anyway.
Yeah.
Confronted with the data, you needed something. Some people always were looking for symmetries and patterns.
Yeah.
But as far as dynamics goes, which is always much harder, just rely on very basic fundamental principles of nature. It's so hard to construct explanations that maybe just general principles will determine the measurable quantities that we confront with experiment.
Okay, before we proceed with Chu and you, and because I want to obviously go into this detail, there are two questions I want to ask. First, well, let me ask them both, and you can answer them. First, as an undergraduate, or as a graduate student, were you in touch, because it was just up the hill, the Bevatron, with what was going on? Because I remember as a theorist, and I was pretty mathematical when I was doing the initial part of my PhD, I really wasn't in touch strongly with the experimental groups at MIT. It was only the latter part of my PhD that I really did. But you were, A, were you in touch with them? And B, you say the strong interaction was these hadronic resonances. There was also the weak interaction. Were you primarily interested in the strong interaction? I guess I'll ask three. And finally, did you choose Chu or did he choose you? So those are three questions I want to go into.
Yeah, so at Berkeley at that time, it was impossible to be a theorist without taking into account experiment, and that was where the action was. And we had seminars, really exciting seminars up on the hill every week, and the lab was up on the hill, but it wasn't that difficult. I had a Vespa.
Because Barry said he had to walk up or hitchhike, so you had a Vespa, so.
Yeah, just to get a ride sometimes with Steve Weinberg, who would also take us up. But I had a Lambretta, and so I could make it up the hill. And I'd go to all the seminars. It was enormously exciting what was going on, not just by the way in experiment, but also in theory. I mean, I can remember some seminars that still stick in my head. I remember Cabibbo giving a talk. So this wasn't the strong interactions, the weak interactions also. Giving a talk on the Cabibbo angle and his understanding of the weak currents.
Sure.
And I remember actually Steve Weinberg asking them a question about SU3 or why not SU8? And it was an interesting exchange. I remember famously a seminar up on the hill that Sidney Coleman, who spent 1 year while I was I first met him. He was visiting professor for 1 year, my last year as a graduate student. He gave a seminar on what was wrong with SU6, the attempt to which led to the Coleman.
Yeah.
What was wrong with trying to construct an extended symmetry, included space-time symmetries, rotation, invariance together.
Yeah. Famous disproof until supersymmetry in a way. Yes.
It was an incredible, exciting theoretical seminar.
Well, yeah, he was a wizard. Yeah, he was wonderful.
Professors at the time, Bardacci, had just written a paper with a lot of people wrote very bad papers about SU6.
Yeah, there were famous. In fact,
Sidney just came along and demolished them all with this one paper. And as you know Sidney very well, he enjoyed enormously giving this talk where he essentially, he was so sarcastic in a way.
Yeah, he would have just demolished them with a smile. And but I have to tell you something. I don't know if I ever told you this, but when I taught at Yale, my colleague Physicist who was a wonderful man and a good mathematical physicist, among other things. But he was once apparently some journalists questioned him on this SU6 and all the hype that people were making about this. And he said, what does it imply to you? And he said, it implies to me that Pauli is dead. Because he would have taken the chalk out of their heads, which I thought was a good
role with SU6. And it was something. Anyway, there was very memorable seminars at that time. So those were the theoretical ones, but the experimental ones were, the 8 meson, this thing. Were, and this interacted with the theory because there was this was a time where Gelman was riding high on finding patterns of 3 and then SU6, well, that didn't work. But SU3 was still being tested.
That was his big success and the Bevatron, in fact, I guess.
My professors at the time were Shelley Glashow and Sidney Coleman was there for 1 year, and they were working away at testing SU. And anyway, you had the education I got. One thing I definitely got at Berkeley. If I'd gone somewhere else, I might have become more rapidly the kind of mathematical physicist that I'm almost became later.
Yeah,
much later. But there. In Berkeley, the game was you wanted to understand the data and make predictions. And that was, if you'd asked me then what's the goal of life is to make predictions and then you had every guarantee that they'd be tested.
I'm still a big fan of making predictions.
But what I've learned later, after some time,
we'll get there.
Testing predictions that I sort of made, or at least helped to make. But nowadays it's a little different. You make predictions. Wait 50 years.
It's a little different. Okay, now the second part of the question was, so there was confusion about everything except QED. There was confusion about both what we now think of as the strong and weak interactions. Although, again, in my own style, when I wrote a book about it, for a long time, it wasn't clear how to separate those two things. And I don't know if you want to comment on that, but it was, to some extent, you focused on the strong interaction more or less for a long time.
Yeah. By that time, it was kind of clear what the difference was, although since one understood neither. The weak interaction, in some sense, were easier. They were clearly, even though there was the only kind of effective theory that we now understand. The Fermi theory of the weak interactions is an effective theory. That was a very successful effective theory. It had a lot of arbitrary structure and parameters, but it was an effective theory and could be treated perturbatively and worked very well. The strong interactions were just a mess. There was no theory, period. The only thing one had were general principles, of causality and conservation of probability and the consequences of those very general principles.
Which is what Chu really focused on, although, and I don't know how much he influenced your view.
Not just true. Chu became, but if one goes back a bit, there was a period before that, maybe 5 years before, where all the leading theoreticians were sort of trying to understand better quantum field theory. Because, in QED, you don't really have to understand anything. You have these rules, you just calculate. But that wasn't going to be enough for the strong interactions where the couplings are strong and you can't use perturbation theory. What is field theory? So there's a lot of work, dispersion relations, general principles, a lot of very important stuff was being developed. But much like it is today in again, trying to understand and deepen our understanding of the framework of theoretical physics. But when the data started coming out like mad and people started seeing various patterns then it shifted. And Chu essentially became a kind of prophet for a few years of this movement to try to understand the data and even construct a theory based on general principles that had been elucidated the years before without having a specific Lagrangian or Feynman rules, and even not having necessarily field theory, just the general principles of observables that field theory illustrated as a relativistic quantum mechanical scriptures. And then it went on to become almost a religion. Which, and it's amazing. The essence of that religion were sort of two elements. One was nuclear democracy, which was the feeling that, you don't really have elementary constituents of matter, elementary particles out of which you build everything else. It was very hard to identify what those might be in the case of the strong interactions. You had the proton, neutron, which were discovered earliest.
Yeah.
But then what was special about them? Could you understand? You needed the pions, which were then discovered. But it wasn't at all clear what was elementary, what could be regarded as of what. And Chu had this radical idea that there were no elementary particles. Everybody was equally
well. And what having come into it years later, the summary I got was that everything was made of everything else.
And started, remarkably there was a paper back in 1949, right after the war, of Fermi and Yang, who must have been a very graduate student or just which explained that the pion, which is very light pseudoscalar meson, could be regarded as a PP bar bound state.
Interesting.
So even the pion could be not elementary, but you could then regard the 3-3 resonance as a rather narrow resonance that was discovered as a pion nucleon bound state. But then you could try to turn it around and regard the proton as a 3-3 resonance pion bound state. And in the end, what Chu said is they're all bad. No meaning to that. There's no meaning philosophically to the fields, which you never can observe anyway, just to these particles. And the way you determine their scattering amplitudes, things that you measure in these collisions, is just to impose general principles of unitarity, conservation of probability, analyticity, which is a mathematical way of realizing causality. That was the big formal development of the late 50s. And you put all this together, and it's so hard to find a consistent description that it has all these good features, so it's probably unique. That was the Bootstrap.
Now, so you, in fact, well, maybe that's what you're going to say by the Bootstrap, because you said there were two principles of that religion. One was nuclear democracy, and the second was the Bootstrap. And the Bootstrap is pulling yourself up by your boots, basically assuming nothing and just accept general principles and trying to find the answer without a specific dynamical model. Would that be a good way of describing the Bootstrap?
It really was the belief. It was just the belief.
Belief, yeah.
But the belief founded on
failure.
So, you know,
like a lot of religions, actually. But go on.
Later, so there were mathematical physicists at the time who were working off in a corner. Unfortunately, there was very little communication between those guys and people like me or my mentors.
Yeah,
they were working on toy models of quantum field theory in lower dimensions, which people like me, felt 2 dimensions. Who gives a?
Yeah, which is famous because you've been famous for doing some things in 2 dimensions.
But they didn't get very. I don't think, actually, tell you the truth, the quality of the research in that field wasn't up to par. Then they were also working on general principles of quantum field theory, which had become highly mathematical, and some of them did some really good work. But they totally concentrated on totally uninteresting aspects of quantum field theory.
Now, were you influenced? Well, it's maybe a tautology to ask this, but I mean, were you influenced by Chu at the time? I mean, you were a new graduate student who's susceptible to, or you worked for him, but did you buy it?
Yeah, no, I got very excited by it it took me about a year. It's sort of like communism. You have to get excited by such ideas. But in fact, I attended on the side, I used to like to go to other classes, not just physics. I went to a philosophy class, which was run by Paul Feyerabend, who was a mad German philosopher, a great influence. And he was very entranced. And I wrote a paper on the Bootstrap, which I think I've lost completely, but on the Bootstrap philosophy, which is really. So I found it a fascinating idea.
Okay.
And what, of course, and it still is. I'm amazed that today, in the last few years, there's been a total resurgence of bootstrapism within conformal field theory, quantum field theory. People are now using exactly the same ideas that Chu was postulating. Now, of course, they know very well that there's no unique S matrix, no unique solution. Even just if you're restricting yourself to 4 dimensions, there are infinite classes. So they know that. But they still enormous attractiveness to some people of this bootstrap idea of deriving all the consequences from a specific dynamical theory from general principles.
Yeah, well, I mean,
with modern computers and techniques of conformal field theory today, you can do things that Chu would have, that school would have just found remarkable. Back in those days, in the absence, it's hard to remember. It's like we talked about the internet and the fact that everything is available at a keystroke.
Mm-hmm.
And the same is true of modern computers and their impact on theoretical physics. So these people can do things to implement bootstrap ideas that were just beyond comprehension in those days. In those days, without the numerical power that one has today, one could get almost nowhere. That was extremely frustrating after a while in that program.
Yeah,
then, I realized at one point, and it was prompted by Francis Lowe, the first high-energy physics conference I went to, which was luckily held at Berkeley. In his summary plenary talk, Francis Lowe was a great physicist.
Yeah, I knew him at MIT, yeah.
Really. He said he was summarizing the Bootstrap S-matrix approach to Flow interaction, and he said, yeah, but in the end, all it is you take a general principle like unitary, you put in something on the right-hand side, you get on something on the left-hand side, you put in something on the left-hand side, you get quantities. What have you learned? And that's stuck in my mind. But there other things began to happen that gave one the hope of being able to do what I really wanted to do the most, which was to make predictions and have them work out.
Well, and okay, this is a great. It's kind of interesting, and I'm really interested in that it was Lowe in some sense who got you thinking outside the bootstrap, because of course.
Well, it wasn't just.
Well, I know, but what I meant is it's poetic to me because Gell-Mann and Lowe's paper on what we would now call kind of like the normalization group was sort of it will end up being very relevant to the work that eventually you won the Nobel Prize for. So we'll get there.
Right, but at the time, so in the last year or two as a graduate student, I was beginning really to get sick and tired of the bootstrap because it's a man.
It's not okay. Now, so you
didn't learn anything fundamental.
So you'd already begun to deviate from the true, the revealed truth, and we're beginning to become satisfied. Now so already by the end of your PhD, that was the case. I assume you moved to Harvard right from your PhD, right, to be a junior fellow? Did you go right to Harvard?
Right. I didn't intend to go to Harvard. I wanted to go to Princeton, which and I
eventually made it there.
But then I was nominated by Chu for the society. As you know, you were a junior fellow. You can't apply, and I hadn't even heard about it. I mean, and Chu didn't even tell me he was nominating me.
Oh, interesting.
So I already more or less decided to go to Princeton, but then I got this invitation to go to the society. So I packed up. And
it was the kind of thing at that time no one refused. Since then, people refuse, but at the time, it seemed to me that it was a kind of an offer you couldn't refuse.
Well, yeah. I mean, it was for me, it was such a incredibly exciting intellectually and so sophisticated. I was from Berkeley, which was a very different culture at the time. When I went to my interview, I had to buy a tie for the first time in my life. And it was so different, but enormously attractive. So
yeah. It was, and then by the time I was junior fellow, it was the place that physicists. I mean, I was already in Cambridge, but it was a breeding ground for physics. I mean, there were a large fraction of them were physicists. But
the students now, rapidly know much more about the world than I knew about the world. And there weren't that many physicists in the society. I mean, of course, Purcell was there.
Yeah, great man. He was.
But Adler had been, I guess, a junior fellow, but there were no.
It wasn't the tradition that you guys helped create. When by the time I was a junior fellow, it was like, look at all the, there was a tradition of physicists who had been junior fellows, but it was.
like one a year or one every other year. Ken Wilson, of course, a junior fellow.
Yeah.
But it wasn't as exciting a place. Harvard.
By the way, I often think, thinking about you and your interview makes me think it would have been wonderful. I really wish they had recorded the interviews so that one could look over the years at these young whippersnappers and like you or whatever. And it would have been fascinating to hear now.
Yeah, I was totally terrified. And
me too.
I realized that morning that I forgotten my razor. All I had was a razor blade.
Oh no! Yeah.
And I was all nicked up and suffering. There were all these very Harvard-y, Donnish fellows asking me questions. They were entranced, however, by the Bootstrap. I mean,
that would probably, I can imagine.
Probably what got me in. But I enjoyed it enormously.
Oh, yeah. Yeah. Now, but the reason I'm asking, I mean, Harvard is a different place by the time, I was there many later than you, but was Schwinger still at Harvard then?
Yeah, Schwinger was still king of the mountain at Harvard. But the year I went to Harvard, a whole bunch of people followed me, or vice versa. Sidney Glashow, who was a professor at Berkeley, was hired back to Harvard. Sidney, who was an assistant professor at Harvard, was given tenure and came back from Berkeley to Harvard. And the third of my professors at Berkeley was Steve Weinberg, who moved to Harvard so his wife could go to graduate school and to law school. And so the three of them moved with me.
Yeah. Or the other way around, as you say.
So they sort of moved into the kingdom. And boy, that was fascinating to watch from the side as a mere nothing.
Yeah, because they were the kings by the time I got there, but they were just the pawns when
this place. So it was very similar to something I observed on a safari in Africa, where they took us and showed us the what had happened the week before was a bunch of cubs or young lions had gotten together in a pack and came and killed their father and took over. And this was somewhat similar to it as the king of the mountain, the lion on top of the heap, and all these young jackals came in and effectively drove him out in a few years.
Yeah, and drove him out, and then and the famous story, of course, of Steve Weinberg getting his office and seeing that Schwinger had left his shoes in the cabinet. Phil Dees.
Yeah. Anyway,
but the reason I'm asking, let me just. It wasn't just a personality. The reason I'm asking, and at least again from my studies, and you can correct me if I'm wrong here, is that the first person to really appreciate the usefulness of gauge theories, particularly non-abelian gauge theory, the theories that eventually became the theory of quantum chromodynamics, the strong interaction and the theory of the weak interaction, was really Schwinger. And so I'm wondering, A, if that's true, and B, if that had an influence on you.
I think it's sort of true. It's a little more complicated. So my reading of the history is that after Yang and Mills, which is the middle 50s, there were a bunch of people who found it very interesting. Now, they included people like Sakurai and others who were very much interested, and Salam and Ward and Neyman and everybody who was interested in phenomenology, especially as it related to symmetries. Schwinger, wasn't a symmetry man as such, although of course but he was much more interested in dynamics and how to include non-abelian gauge theories in his formalism. Did he have any influence on me? Have you ever tried to read his papers?
Yeah, no, they're impenetrable. But I was thinking of classes or what?
He didn't, because it was rather impenetrable. And by the time I learned about non-abelian gauge theories, there were no, it didn't have much influence.
Because clearly he'd have obviously had influence on Shelley and Glasgow because, he'd recommended that. What?
Involved in non-abelian gauge theories either. It was just.
Well, it was he gave him a thesis topic that turned out to be pretty good related to, and eventually became non-abelian.
Particular about the Yang-Mills theory that played in.
Yeah. Now, but so were you more influenced by the young jackals then around you?
Because they were, and as was Schwinger, by the way. So, at the time, the big advances and the thing that got me out of into away from S-matrix theory was that big advances were happening with spontaneously broken chiral symmetry. That was the big breakthrough of field theoretic techniques that understanding spontaneous symmetry breaking.
Yeah, and for the listeners, that's the fact that the underlying theory represents a symmetry between left and right, but somehow the states that are manifest don't, right. And that's the case in the world around you. Both of you, if you look at you and me and our surroundings behind us, left is different than right, even though we kind of feel like there's nothing fundamentally different. But so the circumstances in which you find yourselves can violate that fundamental symmetry, and that was obviously a very important central idea, and that was just developed around then, Nambu and others.
No, it went back earlier, but the big advance was to understand that the consequences of that, the whole, which led eventually to understanding effective field theories and
Weinberg, I know at the time was writing lots of papers on, using chiral, what we would now call chiral perturbation theory.
Weinberg was in current algebra, so-called the behavior of currents that are the sources for these symmetries. This was understood then. There's a transition from understanding that as a product of symmetries, to dynamics of the strong interactions. There were some rules that were being derived and compared to experiment, the Adler-Weisberger sum rule. This was directly learning about the strong interactions in ways that were trustworthy, but they weren't bootstrappy. Okay, and
so what was the most exciting work that you did, you think, while you were junior fellow?
At that time, was taking cognizance of this and trying to bring it into his framework. And these younger guys who were working on this, including later me, were it was a bit weird. And but Schwinger suffered a lot because he had, was a recluse and had his own point of view, and everything had to fit into that. And then he switched to trying to fit into his way of looking at it, which really wasn't different. It was just a recap of the same principles in different language, everything that other people had done. So it didn't.
Okay, it's not for Schwinger now. I want to talk about you. So what did you do that, if anything, that you were proud of while you were in the society?
So I was very interested in these. I was still working on S-matrix theory every once in a while, and there was also a time where, by the way, string theory began at some point.
Yeah,
I was also involved in the beginnings of that, but mostly I was concentrated on these currents, because partly because of my upbringing, you were told part of the true philosophy was you shouldn't discuss things you can't observe. You should really be a pragmatic physicist and only talk about what is observable.
Yeah, well, it's not such a bad.
It's a very important principle in the early days of quantum mechanics, where many classical things you might talk about were not observable. They contradicted. But here was a different issue. Fields are not observable, only particles. That's what's observable in collisions. But currents were observable. So you could discuss their properties. And I got involved in the idea was to go beyond just using the charges, the generated symmetries, those are integrals of currents, to the local properties of currents, what we would call today operator product expansions. By making assumptions about those, you could derive some rules, which went beyond just testing for symmetries, which were going over and over again, symmetries. And those symmetries, we now understand, are kind of accidental properties of the strong interactions, and they don't teach you very much in the end. But the currents could actually give you dynamics. So I studied those, and perhaps the most important thing I did at Harvard was explore various, what we would call models. Today you'd call theories of the strong, gave rise to different properties of the currents. But these currents are really observable, and there was an accelerator that was being constructed, which among the rest could measure correlation, these currents, and at SLAC. And Callan and I, the most famous was the demonstration by Callan and I of the polarization of electron-proton scattering to.
Was Callan at Harvard? Or he
was an assistant professor.
Oh, I didn't realize that. I knew of you at Princeton together.
We worked a lot together at Harvard. Most importantly, we showed that you could easily distinguish between theories models, like the quark model, where the constituents of the proton had spin 1/2, like quarks, or spin 1, spin 0.
Yeah.
And so that's the so-called Callan-Gross, and it was almost immediately tested, because as the experiment came on, they did indeed discover that it looks like the proton is made out of quarks. So,
no, I remember, I think being tested on
some rules to, when I spent some time at CERN, to show that the experiments again indicated that the things that made up the proton didn't have just spin 1/2. They also had color. They also had. They looked like quarks.
Yeah, no, this hits home for me in an emotional way, because
enormous impact on me. But there were a lot of other things I did. I almost got the Veneziano model.
Really?
I was playing with, along the lines that the people in Israel were doing as well, trying to construct functions. This is the Bootstrap functions that were crossing symmetric, and I got very interested in that when that happened, when Veneziano found the beta function, which did all that, and a bunch of other things.
But that Callan-Gross, what's interesting for me, and because it is a way to try and connect the dynamics to look for fundamental physics, and it's emotional to me, because after I failed my first PhD oral because I was too mathematical and I didn't know what was going on, I remember studying intensively to try and understand the phenomena, the physics behind the quantum field theories that I was interested in. And learning about what the experiments were that told you that quarks were, might have color, spin 1/2, et cetera, et cetera. So it's bittersweet. Well, it's sweet because I eventually passed, but it was a traumatic time. But now, did you move? Did you spend some time at CERN while you were a junior fellow, or did you move? Yeah.
It attracted me as to go to, instead of Princeton, was that you'd get a year off.
Yeah.
I took advantage of that, took half a year off at CERN.
Yeah, I remember.
Great place to be, and this was already 68.
Yeah, so it's a great place to be.
exciting place.
But then you finally made it to your Shangri-La. You finally got to Princeton, where you'd always wanted to be. From there, right? You became an assistant professor at Princeton.
Yeah, right. Again, there was a lot of choices, and I was tempted to go back to Berkeley, where I had an offer, and that was always my dream, to come back to California, which I finally succeeded.
Took a while.
But Princeton, was really, yes, exciting for the physics at the time. And so I went to Princeton.
Well, it was a pretty good place for you to go. And you now this was 1968.
So I was, at that time, there were two things that totally obsessed me. One was this deep inelastic scattering, which was the way to test the properties of these products of currents.
Which, again, let me just say for the listeners, was really just a way of trying to look at the scattering of particles like electrons, which would scatter off a proton and reveal facets of the proton.
Yeah, I mean, this was very energetic, using the electron as a microscope to probe the structure of the proton. And an experiment where people didn't expect much to happen. The proton would be smeared out object, and okay, you'd see it smeared out, big deal. Very much like what people,
Rutherford
Thompson thought Rutherford was.
Yeah.
Never bothered to ask him what he was doing. But Rutherford found protons inside the nucleus of atoms.
Yeah. I know, because I've heard you talk about this. You were, at least as you said then, I assume you're going to say the same thing now, is you were trying to disprove that any simple quantum theory would work, and instead.
So the main thing is, I just thought this was absolutely fundamental measurement. Discovery of this point-like structure. So, or what looked like point-like structure. And not only that, it was quarks, because that I was wedded to, not so much. But the experiments and the strong interactions were never clean, as they are in the case of the weak interactions, which is why many of my theoretical colleagues would just concentrate on the weak interactions, because it was a lot cleaner. But if you looked with a biased eye of somebody who had written down, managed to put forward some conjectures, which were then more or less plus or minus 20% verified, convinced me that this was a theory of quarks. And that was just crazy, because there weren't any real quarks. So what was going on? And then point-like behavior. So I was convinced this was essentially enormously important. And that was shared by a lot of people, but not totally. Partly because there was no way of thinking about it.
Mm-hmm.
There was no framework in which you could understand any of this in a fundamental way. And partly because, experiments, when the discoveries are first made, they're big errors.
Yeah.
It could easily be wrong, and it could be. So, but I was obsessed. And at that time, I was influenced by a lot by Ken Wilson, who I met at Harvard, partly because Roman Jakif, who was somebody I worked with, was a junior fellow with me, was his student, and his ideas were just enormously exciting. And the renormalization group, which at that time had been developed, a perturbative renormalization group by Callan and Szymanczyk, which I knew very well because of Callan, and even more so by Wilson's renormalization group.
So you learned about the renormalization. So his ideas on renormalization influenced you. I was going to ask if
I knew about him before there were papers, because he would come often to Cambridge, where his family lived.
Yeah, his father was a professor there. Mm-hmm.
and he would come by, and Roman and I would talk to him. Nobody else would, but we would. And then famously, I brought him. He was on sabbatical at Princeton in '71, where when he was just developing these ideas, and I famously got him to give a course, which became a physics report. I got John Kogut to.
I didn't know that's how that physics report.
Forced him to take notes.
Wow, anyway. I didn't know that. I knew the physics report, but I didn't realize the etymology of that.
Yeah. So and those lectures that Ken gave were very important historically, because that's when his ideas became public. And
were they important to you, though? I mean, so basically
they were important. I was very close to Ken at the time. We were playing games. Numerical. We were studying the structure. We were looking for limit cycles, looking for all sorts of things. But it was all based on old-fashioned computers where you get the cards. He was very good at that, and I just went along. But it didn't lead anywhere. Again, modern computing has truly changed the way theoretical physicists are able to work. But anyway, but that gave me a plan to deal with this thing. I really wanted to see whether I could, to understand asymptotic, what we now call asymptotic freedom, which is a way of getting point-like behavior. But,
did you know? I mean, hold on a second. So I was going to ask you about this, but anyway, it's interesting. I don't think I've ever talked to you about it. But, so did you, in advance, you knew that the only way to get the quark-like the behavior that was seen in diplomatic scattering was to have something like asymptotic freedom, or did the realization occur after you discovered asymptotic freedom?
No, it happened along the way.
To be
totally obvious, since most people didn't think it was obvious. Ken Wilson didn't think it was obvious.
Sure.
But he thought it would, one, he didn't take the experiments, weren't, as I said, so you didn't have to believe them. There could be anomalous dimensions, they could be small, they could be, whatever. Experiments were conclusive, and the few people who understood how to ask the question of this type were divided. And there's certainly no proof of it. And so my main goal was to show, it was a way of narrowing the kind of theories. And it really meant quantum field theory, since there were no other theories.
Yeah.
Except the string theory, which had been developed already in 68, 69. And which I was enormously interested in, and spent a lot of time and did a lot of work on that with Schwartz and Naveau and Shirk at Princeton. It was for a year or so I was totally just doing that one. It was very exciting, but I did realize that could, string theory is worse than quantum field theory. Very soft at very high energies. It doesn't give point-like structure. After all, strings aren't point-like; they're extended.
Yeah. And by the way, again, I'm just going to interrupt just for the listeners, because we're talking things, and I mean, I'm assuming many people listening to this know what asymptotic freedom is, but it wasn't what was fascinating about the SLAC results, which were recognized for a while. And I think maybe Bjorken was probably one of the early people to recognize this, but it was not just that there were point-like objects inside the proton, but what was really weird was they acted like point-like objects that were not interacting very strongly with one another, whereas the whole point of the strong interactions were the interactions strong. So how could you have something be made up of particles that looked like they were relatively freely banging around inside the proton? And that's what appeared to be the result of the SLAC experiments. Anyway, I just wanted to preface that for people.
So you could, one way of describing that would be to say that you have Proton is made out of quarks, point-like objects, and they interact very weakly. But that, of course, is crazy because then if you hit the proton with a hammer or another proton, those quarks are going to escape, just like electrons escape, get ionized, escape from the atom when you smash something into it. And they never did, no matter how hard you hit them. So something was very weird. It could, anyway, one explanation could be when we realized that how particles interact depends on how close they are together. That can change, and there are ways of understanding how the strength of the interaction between particles changes with distance. That's this renormalization group approach. And with that tool, I realized, okay, well, I could try to understand whether you really need to turn off the interaction as you go to short distances to explain the phenomena. And if so, then you could examine, using weak coupling techniques, whether that happens in any theory one could write down. And the list of theories that are sensible, I knew were a finite, well, not a finite, but a denumerable set that one could maybe get a handle on, all possible theories. Anyway, that was the plan, which I started to work on maybe at the end of '71. And one aspect of that, which I thought, was probably the hardest, was to sort of see whether asymptotic freedom was necessary. And there'd been some partial work on that by Parisi in a class of theories, and Callan and I worked on that and extended that to all theories except these non-abelian engaged theories. And then the other part of the program was to see whether there were any theories which had this property of asymptotic freedom. And that I worked on alone. But at some point, I was dealing with a nasty integral inequality I couldn't prove, and Sidney Coleman helped me, and we wrote finally a paper showing that there were no such theories. Once again, excluding these complicated engaged theories. That was sort of in hindsight, there wasn't the intuition that one could have had, saying, okay, well, most theories have the coupling gets weaker when you move particles apart because the force is screened by other particles. And then maybe if I want for the force to get stronger when I go to pull them apart and thereby weaker when I pull them together, I want something like anti-screening, and how can I get anti-screening? So anyway, that is not
that in retrospect, that's how we now explain it, but you're right, the intuition was never there in advance.
Well, the intuition wasn't there, and the non-abelian engaged theories were not discussed directly in either of these elements of this program because they were too unfamiliar and difficult to do. Nobody at that time, Ed Hooft and Veltman famously developed the formalism so that they could argue that the theory was renormalizable, but nobody was calculating these higher order quantum effects, which would be necessary to get this phenomena. So what I had to lose, and that was the final part of the story, which led. So indeed, it's correct that I suspected that there were no such theories, that even non-abelian gauge theories would again not be asymptotically free. And this was sort of back to Chewian days, if you want. I would show, this would be an experiment that I could show implied that no field theory could explain. And as somebody who had grown up with that, had been interested in that to begin with, and also was fascinated by string theory, which couldn't do it either. Anyway, I was, my expectation end kind of hope was that I could kill quantum field theory.
Where instead you saved it, of course. But well, that's an interesting. I'm really happy to hear this because we've talked and I've heard little bits, but it's nice to, I don't know whether deconstruct is the right word, but to probe in detail what it's hard. And again, after the fact, it's always hard to remember your thinking exactly at the time. But you decide to work on it, and it was a formidable calculation to do because the theory was new. The kind of theories hadn't, the techniques that were developed later on to make those calculations simpler weren't yet there, and you had to do this incredibly complex calculation. And is that the reason you? Well, I'm going to ask you. So you did have a graduate student that you brought on at the time and
Frank was my first graduate student.
Yeah. Which is a good beginning.
No problem. I said, well, besides which, my strategy was always graduate students were sort of controllable collaborators. All my students always worked with me. I mean, I didn't have problems. Come out and work. But it was tricky. So, for example, one of the tricky businesses was that we were calculating this function, this beta function, that controls how physics changes as you scale things upward. And it has to be independent of this theory has a big symmetry, gauge symmetry, and anything you observe has to be independent, invariant under the symmetry transformations. So really just reformulations. They're not. But intermediate steps aren't, and it's how it ends up being gauge invariant. So we had to be very careful. Anyway, yes, today it's a homework problem in elementary course in quantum field theory. Experimental physics, today's discoveries are backgrounds.
Yeah, exactly. Once, that's a great story about physics. The great discoveries becomes backgrounds once and that's true. But so because though it was a complicated calculation and it was great and lucky, it was lucky for Frank to come at the right time, but you were lucky. Frank was a pretty good student too. But when you came up with the answer, as we would say technically for the physicists, the beta function was negative, but for the rest of the world, that this concept of asymptotic freedom, that the specific set of theories had the property that was necessary. First of all, were you skeptical? And second, were you how much back and forth did you go through? Because this is quite a statement to make. You have to be pretty certain you're right.
Yeah, it's quite a statement. In our first paper, the discovery paper, I actually wrote down the Lagrangian and said this has to be it. See, it wasn't just that, but the thing. Well, there were two aspects of it. One was when you, together with these other things, these other elements that work with Coleman and Gallup, there was a unique theory that could have this property, and that was based on this generalization of Maxwell's theory with many charges, with more than just one electric charge. But then once you look, try to apply this to the real world with quarks, then you said, well, it has to be a theory of quarks interacting with this generalized electromagnetic chromodynamic field. And what are the charges? Well, already people had identified that these quarks had to carry a label, a charge, didn't play any role necessarily, but it had to be there to account for how you count combination of quarks.
In statistics, yeah.
Statistics of the proton, for example. And so one already had three colors that had to be there for SU3. And that is about it. Aside from the mass of the quarks, there are no other parameters in the theory. So immediately one could say, not just has to be a theory like this, had to be this specific theory, period, nothing else.
Yeah, and that was
furthermore, once you said that, everything, just about a lot of things that made sense, that were part of the lore of trying to build understanding of the phenomenology of hadrons, of strongly interacting particles, fit in naturally to this theory. That's on the one hand. My God, that is a real never forget. But second was immediately, if you're going to take this seriously and say this has to be the strong interactions, I could write down the equations with just the masses of the quarks as parameters, period, that's it. Then somebody says, well, where are the quarks? So immediately, first, problem was, where are the quarks? How are the quarks? Why don't they ever get out? Now, people who had believed in quarks, it was hard not to believe in quarks because it looked like there were quarks, said, okay, well, they're quarks, but you can never see them. They're confined somehow. They can never get out. And it was enormously exciting to realize that if the force gets weaker at short distance, it gets stronger at large distances. And maybe that can keep the quarks from ever escaping.
Maybe.
But at the time, one, we didn't have understanding of asymptotic freedom and its physical origin. Two, there were no models of confinement, no examples. There are analogs that are quite known in physics, like magnetic monopoles, but nobody had made that connection either. So at the beginning, it's really scary. And so this discovery, which happened very rapidly, realization there's only a unique theory could explain, everything fits in, everything we know about chiral symmetry breaking, patterns of quarks. But on the other hand, there's this totally weird phenomena of confinement. So to contain both of those emotions of exhilaration and fear at the time is really strange.
Was it a eureka moment? I mean, did you feel like when you got the result and you were convinced it was right? I mean, I'm sure there was some time when as you say, where there was a lot of finagling and saying, well, did we get it right? Did you just say, this is amazing? Did you realize it was going to, I mean, I hate to put it in this terms, but did you realize it was a Nobel Prize winning moment?
Well, as I said, there's the exhilaration part.
But you knew it was significant. I mean, you knew it was really going to change things.
But yes.
Okay, but you had this fear, and it's your perfect segue, because I was going to go from that to confinement. I was going to go. There are many, and I must admit, when I first met you, I have to admit, it was at a time when you were with several colleagues at Princeton, had been working on an idea that might explain confinement, and it was the hot thing at the time. And I went to attend a summer school, which is where I met you, and you got through. All three of you talked, and were very excited because you were pretty sure you were on the verge of another breakthrough, and which didn't happen, and we still don't have a fundamental proof of confinement. So I wanted to ask you. I mean, no one doesn't believe it's confining. It's one of these things, but an analytic proof doesn't exist, and I think there's a big prize, $1 million prize maybe for it. Do you think there will be? I want to get to Lattice QCD in a second, but do you think there will be ever an analytic proof of confinement?
Well, I'm not sure what that means. There are so many things that in physics that haven't been rigorously proved.
Yeah.
So, confinement is sort of at that level now. So, for example, anyway, that became my next obsession, having gone beyond.
Sure.
The first goal, of course, was to use this theory to do what I really wanted to do.
Prediction. And a beautiful series of papers with lots of predictions came out by you after.
Deep question was confinement, and what I wanted was not so much a rigorous proof of confinement, that Clay Millennium Prize, $1 million QCD, but
but a physical argument.
Well, there physical argument, physical understanding, and a controllable way of calculating properties of hadrons. Now, today we have, as far as understanding this phenomena of confinement, where you have a theory, used to have big arguments with Wigner at tea time, we would say. You can't have a theory based on particles that don't exist as asymptotic states. You can't take out of the proton. Makes no sense. They're unobservable. Anyway, but we do have an understanding of confinement through many analogs or models that confine that can be solved exactly. I mean, it's not a strange phenomena anymore. It's standard, it's ordinary, it's explainable. But QCD is a complicated theory, and it's unlikely that we'll ever have analytic solution of anything in QCD. It's conceivable there'll be well-devised approximation methods, and that's what we were really certain, what I really wanted, was a way of making pretty good calculations or arbitrarily improvable calculations. That, to some extent, has been achieved by use of modern computers. It's called Lattice QCD. You truncate the solution to a finite dimensional thing, and then you take the limit where you cut up space into points on individual points of lattice, and you take the spacing of those points to zero in a way that the theory tells you how to do, and you can calculate now to a precision of better than 1% the spectrum of all those particles that were being discovered at Berkeley. This was my dream. It has been achieved. And in that formalism, quarks are confined. So if you want that formalism of QCD, which in this way of doing it exhibits confinement, also has, as many tests as you want of complicated spectrum and scattering phase shifts of hadrons.
To what extent, let me jump back and as a devil's advocate and say, to what extent it exhibits confinement, but to what extent is it an input in lattice gauge theory? In some sense, confinement is a input into lattice gauge theory in term.
You could see it, Phil. You could pull these quarks apart and instead of getting
you can measure the.
Within this formalism, it is verified. Now, if you ask, okay, well, you haven't taken the lattice spacing to zero, and you haven't taken the quark infinity.
It doesn't matter to me. Yeah.
This is at the level of the kind of rigor which is wonderful. Physics should always try to do, but it's never been my life goal to prove rigorous theorems. And the physical understanding of confinement is to me, quite clear. The method we were trying, which was based on semi-classical approximations, taught us a lot about instantons and non-classical saddle points to these complicated integrals, but didn't lead to a controlled approximation in the real world for QCD with 3 colors and so on. All other analytic tools have so far failed. There's still some hope.
Okay, well, I want to ask you. I'm glad we got the lattice gauge theory, lattice QCD, like I wanted to, and I wanted to ask you a very topical question in that regard, your opinion, because I just prepared a little public explanation of the Muon G-2 anomaly, which if true is very exciting because it points to physics beyond the standard model. But what is equally interesting is a new calculation using and it's wonderful to see lattice QCD come into its own in this sense, which is accurate enough to be able to apply to this problem where you need to know the result to 1 part in a billion. It tends to disagree with the other ways of using it, which is to use experiments and plug them into perturbation theory and try and estimate what happens. This direct lattice QCD appears to agree with the experiment. So I wanted to ask you what you thought about that and whether you think that'll be the result or whether the G-2 is really sign of something new.
I don't know.
You don't know either, but what's your gut feeling?
So the lattice QCD calculation that was done that is somewhere between the previous, collective calculation, which uses experiment, but then it requires analytic continuation to get it. So it has errors as well.
Yeah. Yeah, but it is interesting that it's close to experiment. So, it's hard to know. I'm agnostic about it to some extent. I'd like it to represent something fundamentally new and beyond the standard model, but I don't know for sure.
Yeah, no. So, but this is something under our control. This doesn't require a machine. This requires more calculation on both sides, which is being done, of course, to try to narrow that theoretical. But it is a lovely situation where the discrepancy is, in both cases, even taking that lattice QCD calculation is in disagreement with the experiment, just not by 4.2 sigma.
Yeah, but not by enough to be a golden. Yeah, it's intriguing. And the good news is the experiment is going to I think they've only analyzed 6% of their data, so the experimental uncertainties will go down. And
experimental uncertainties go down, the theoretical uncertainties will go down.
So should we make a bet whether it's new physics or not?
This theoretical calculation is only one group has done.
Yeah.
And so since they were able to do it, I mean, it's an extraordinarily impressive calculation.
Mm-hmm.
It really wasn't. Will be done again for sure because of the importance. Mm-hmm. And we'll wait.
It's fascinating. It is the most exciting little bit of particle physics that's happened in a long time, I think.
But remember, for going back, in my younger days, I was interested in trying to calculate the electron-proton mass difference. Proton-neutron mass difference.
Yeah.
Which now the lattice has been calculated to less than 1%. Yeah. It is amazing.
Yeah. It is remarkable. Again, and
that is not as exciting as an analytic calculation.
Yeah. But it's fascinating to see. It's something I've lived through. It's something I can appreciate, seeing the change from when I was a graduate student to now. Well, okay, so we've now done QCD. We talked about it, but now, and we're gone on so long that I find it fascinating. But it would be a shame not to get to string theory, which we'll get to briefly. But one thing did intrigue me, if I think about you. So the fads, and I don't know whether you want to call it fads, but the focus of the herd was sort of on the strong, ultimately the standard model and the strong interaction, and then it moved to grand unification for a while. But I don't know of you working on grand unification directly. Did you work on grand unification?
Well, so I was, after QCD, was totally obsessed with trying to develop, understand QCD in detail. But towards the end of the 80s, 70s, beginning of the 80s, definitely I was not so much focused on grand unification originally, George Aglashow, et cetera, et cetera. I actually didn't have much faith on such a simple extrapolation. But it was a striking fact that the coupling, that the indications were that there was this enormous scale. But I think I turned to it partly, I was more interested in supersymmetry and string theory.
Yeah, but even at that time, in the late 70s, early
80s especially.
Yeah, but the heyday of the classical heyday of the string of guts was sort of late 70s. And the initial models, the discovery of the fact that, hey, the coupling constants seem to come together if you made this wild extrapolation.
That was discovered quite early. That was more
in 74, 75, I think.
Exactly. Yeah, no, I guess I just didn't have much faith in that. Uh,
I can understand it. It was a big extrapolation. Not as big an extrapolation as make for string theory, but it was a big one.
wasn't just a big extrapolation. It just sort of didn't. I mean, it made a lot of predictions, like proton decay,
Yeah.
but it didn't have anything new in it.
Okay. And that,
The other thing that I became more and more convinced was you see, QCD was a truly remarkable theory, which I always was very proud of, was that essentially no parameters.
yeah.
It's a complete theory. Whereas the standard model, the Higgs sector of the standard model, as well as QED, had,
Yeah.
asymptotically free, and there had to be some new physics at the ultraviolet.
Yeah.
So grand unification was clearly alluring. The couplings did seem to come together. Something was happening. But just putting things into a SU5, SO10 group didn't solve that problem.
Well, and I don't know if you felt the same way as a graduate student. That was the kind of thing to work on. I didn't work on it either. I kind of by that point, what happened was that, yeah, you had this sort of kind of natural theory called SU5, which looked like it was the simplest possible wave, but then it wasn't clear that that worked experimentally. And then it became a matter of finding more and more complicated groups. And that to me just didn't attract me at the time. It was just inventing the wildest, craziest, largest groups to do things. It just seemed.
Six.
What?
Like E6 or E8?
Yeah, exactly. Like E6 or E8. It just seemed like frantic, just an excuse. It was an excuse to get PhDs, I suppose, but I didn't.
It was very interesting. There were other issues in the standard model that you might have hoped, if you unified things, you'd get some insight into, like the spectrum of flavor and masses and mixings, but didn't happen.
Yeah.
So there wasn't much coming out of this. And again, I was always more interested in dynamics, and there was still, you had this problem of what we call today ultraviolet completion. Then there's another thing that motivated me and many others, but it certainly was also happening at Princeton, remember, which was interest in gravity, quantum gravity as a part of nature. It's something field theory should think about. Hawking's ideas, Euclidean path integrals, and supersymmetry, and string theory. Because, I never lost my interest in.
I was going to say, you never lost your interest in theory. It's dynamics. So even before the heyday, you were fascinated by it.
Yeah. And I always had a connection through John Schwartz, who was always, So string theory was developing very slowly.
Because you and Schwartz had worked together on other things early on. Is that right?
And we worked on string theory together.
With Neveu and others. Okay.
So and John his mother lived in Princeton, would always come to Princeton once or twice a year. And I would meet with him. And Ed Witten also was kept interested in string theory at that time. So, in fact,
did Witten push your own interest at all? Did he reinforce your own interest, or?
Not particularly. Well, more in thinking about unification with gravity, anomalies, that whole story. So it was clear from the unification of the couplings that something interesting is happening very close to the Planck length. So it became clear that you have to think about gravity. And I'd worked a lot on solitons, instantons, and played around with those ideas, did some nice work.
Yeah, you did some nice work.
The decay of hot, flat space. Anyway, there are all sorts of interest. So it was thinking about quantum gravity. But these were on the side, and they got more and more out of tired of not succeeding to get a controllable calculational tool for QCD, and not willing to do that as QCD. It's not my cup of tea. But I got more and more interested in unified theories with gravity and their problems, and string theory.
And you quickly became, you certainly quickly became not just did your work become central to making a quote unquote phenomenological, at the time, phenomenological theory of string theory that looked like it might be a theory of the world, but you also became a zealous advocate for the approach, would you say?
So in 1983, I went on sabbatical to Paris. And
I remember I met you there for lunch once, but anyway, it doesn't matter.
Anyway, my plan there was to get back into string theory, seriously. And I was going to work with André Neveu. But André had got a job offer from CERN and was not in Paris, so I did other things. But I was also, boning up on what had been done in string theory. Not much over that 10 years. It's been very slow. Only a few people working on it. But still, it was impressive. And then the year after, this explosion happened. So I was in a good position. And there weren't very many people who knew anything about string theory. And I was teaching a special topics course at Princeton that year. And I'm not sure what I would have taught, but I decided to teach string theory. And boy, that was just about everybody.
And teaching a course is, I don't know for you, but for me, teaching is the one way to really understand things.
Yeah. So that was a very exciting period.
Yeah, 1984 was the string revolution, and looked like all the problems in fundamental physics be solved, and were people, and I don't know if you were one of these people, but there were people who were saying, yes, the future is here now, and we're on the crux of knowing.
Yeah, so one of the most exciting elements of string theory remains to some extent, is that every parameter, so, in physics, we write down equations, we have Lagrangians, we have Hamiltonians that dictate the interactions, that dictate how things work. And there are all these parameters that are in these equations, like the charge of the electron or the mass of the electron. And in quantum field theory, by and large, those are free parameters. And it's always annoying because physicists like to calculate everything. To have free parameters that you could adjust, or somebody God adjusts, or what, you don't understand how to calculate is very annoying. The great thing about string theory is that in some sense there are no free parameters, in the sense that every parameter you might insert into the solutions of the theory is dynamical, has dynamics of its own, and might be determined by some dynamic. And so that was enormously appealing. Going back again, bootstrappy if you want. This is better than Bootstrap.
Now,
close to that, very close to that. If you throw away the core, no problem. So that was enormously alluring. And of course, we've understood things are slightly more complicated, to say the least. But at that time, in '84, there was a feeling there were only 5 theories. And all possible parameters that we observe at low energies in our standard model could be calculated.
It was incredible hubris, incredible excitement, and incredible hope. That hope hasn't obviously materialized. And it engendered lots of sharp discussions, and I don't think it's necessary to go into those, nor can we do string theory justice now anyway, but But let's go. We're 30 years later, more than that, almost 40 years later. Which is weird to think, isn't it, David? Almost 40 years after 1984. And it is, would you say it's a success or failure, or neither?
It's, of course, a success. I mean, success is.
I knew your answer, but I just wanted to hear why you'd say it.
Right?
What?
And when you're climbing a mountain in the dark, which is the way I picture physics, exploration in physics is climbing a mountain never seen and is covered with clouds and it's dark. Okay. As long as you're going up, it's good.
So you think we're going uphill? Do you think we're still going uphill when it comes?
Except the focus has shifted a bit. So there are no parameters in the basic discussion of strings, but they've sort of reappeared as boundary conditions.
Yeah.
Choose particular solutions. But the main breakthrough, the main advantage, change of attitude is that string theory is no longer separate in any way from field theory. It's not like it's a different part of a bigger framework and it includes them both. And so, back in '84, we were operating under a traditional point of view. There would be a theory which you could write down, just like you do in quantum mechanics or you do in quantum field theory. You write down a specific theory, like QCD, and then you solve it or test it. But you never had that in string theory. You just had ways of constructing solutions of something, not a theory, but solutions which were consistent with general principles, if you want Bootstrap. And it was somehow different.
It certainly is different. Let me make a statement which you probably won't agree with, but let me make it anyway, and you can refine it. Is it fair to say that string theory has not succeeded in achieving the initial claims and goals of the theory, but it's been incredibly useful to the physics community in developing a new way to think about many aspects of physics? Would you say that that's a true statement?
Yeah, that's sure. That's certainly, I wouldn't say that's all. It's much more. See, I don't think string theory isn't a theory.
Yeah. And that's why I never thought it should be called a theory. It was a mistake. But anyway.
Framework. But quantum field theory isn't a theory either.
Exactly. That's the reason. But people don't realize that. The public doesn't.
QCD is a theory.
Yeah.
QCD is a specific theory in the framework of quantum field theory. By the way, QCD is also a string theory. We now understand that there are these dual descriptions.
Yeah, that's one of the fascinating parts.
In a sense, when you confine quarks, they create a flux tube, behaves like a string. And in close cousins of QCD are undeniably string theories in hyperbolic bigger space, ADS, anti-de Sitter space. We now know that string theory and quantum field theory can often be different ways of looking at exactly the same phenomenon. So quantum field theory is a lot richer than we ever imagined.
Yeah.
And theory is an extension of that framework. What that framework is, the framework of theoretical physics, the fundamental framework, is something we do not know how to describe at the moment. But it certainly contains both what is called string theory and quantum field theory. And what the rules are, we don't know either, to tell you the truth. Especially since some of these descriptions, and the ones we're most interested in, contain quantum gravity, contain gravitational physics, which at the quantum level is really demanding of us forcing us to confront some of our most basic notions of space and time and even causality.
And like happens at any exciting time, I suppose, if it is exciting, that always happens at the frontier of physics, which you never get a sense of when you read the history books because it's all described as if it was logical, coherent after the fact. It's confusing, and I think it's fair to say that what reigns right now is a lot of a lot of claims and a lot of confusion, and we'll see where the dust settles. Would you think that's a fair thing to say?
Well, there's just no. So there were people, some of my good friends, who would argue that string theory, which they thought was a normal theory, is a waste of time and a failure because one can't calculate the mass of the electron, and it isn't motivated directly by experiment. But string theory, as I said, is the standard model. There's no question about it that in fact, I just got a paper from one of my students, ex-students, who was making big advance in towards constructing the dual string theory representation of QCD itself. I think that will happen. I'm not sure how useful it will be as a calculational tool, but it will happen. So
I think but it's fair to say, look, one could go back and forth. This all
structure of theory, string theory is part parcel.
Yeah. Okay, I'll accept that, but I think part of the reaction was simply the claims that the expectation appeared as if 1984, like we will calculate the mass of the electron and therefore just wait, and that was unfortunate.
You're close, but yes, and so what's missing to be able to do that is totally unclear. And so to some extent, what's happened for the last 30 years or so now, almost 30 years, 25 years, has really been just exploring the framework and the connection between different ways of looking at the same phenomena to enrich our understanding both of standard model, ordinary physics, standard model, head string, and gravitational physics, if you want.
Okay, well, look, this brings us to the present, which is, as you say, I think puts it in perspective. Obviously, we could go on about that, but right now we just, as you say, we're hoping, and people are working, and there's lots of areas, and we'll see what the future is. But I don't want to interrupt you if you want to say one thing before I move to something else.
There are great successes,
Oh, sure.
Deep paradoxes in trying to apply quantum mechanics to gravity, which have been around for 100 years. And there, the combination of this enlarged framework is solving a lot of those problems.
Well, it's giving us new ways to address them. I guess I'm not as optimistic that it's solved them, but it's certainly giving us new ways to think about them.
I'll give you an example. Hawking famously claimed, quantum mechanics fails when you marry Einstein. And okay, and that isn't true, and one can demonstrate that without any question in simple examples of black hole physics.
Yeah, in simple examples, but let me ask you a question. I don't think we have resolved the fundamental paradox of black hole information loss. It's clear. I think people are optimistic, but I don't think there's a clear what.
If you announce a paradox, you say, okay, a black hole violates quantum mechanics. And of course, there are lots of black holes, including the big ones that are in the center. And then you have this theoretical framework, which we all believe in, all of the aspects different, and which for certain black holes that I can construct in my mathematical lab do not violate quantum mechanics, for sure, then I have shown that the arguments that lead to that paradox are simply invalid. And in that case, and in presumably every case, since we have good evidence for quantum mechanics, the responsibility here, much like in trials, is
proof.
prosecution, not the defense.
Okay. I didn't come here to praise string theory or bury it. But
Hawking, in the early stages of the application of duality to the information paradox, gave up.
yeah, I know. But, physics isn't done by democracy or voting. But
by raising a question mark and saying these two are incompatible, you have the responsibility
sure.
to. That's universally the case. It's not just maybe it's invalid because you haven't in every possible case. Come on.
Absolutely, I agree. No. Look, I think the point is clear, and I agree with you. Let me ask you two or three more questions to end this. I want to talk about the future a little bit, but not the future related to string theory. But I do have to ask you something I've never asked you about, I don't think. So Wilczek and Witten were both your graduate students. And I think most people of my generation would say that they are among the two of the most preeminent theoretical physicists in the generation, but sort of semi-generation after you. Yeah, I mean, but they're certainly among the top.
Oh, absolutely.
And is that just luck?
Well, I don't know. I don't think it's.
I mean, look. What's clear to me, in having been a faculty member and a student, is that students move to the people who are doing the most interesting work. So it's not surprising that perhaps they chose you. What?
Smartest students.
What was that?
Especially the smartest students.
Yeah, the smartest students tend to know who are the interesting people and try and work with them. And sometimes the people who agree to let them work with them. That's not always the case. But I think I remember you famously, and I think this is true, and I can't help but say this story because it relates to the Society of Fellows, where both you and I and Ed was a member, is I think you wrote to them a single line recommendation. Didn't you say something like, this guy is smarter than me and he's smarter than you? Take him. Is that true? I heard that somewhere.
About who?
About Witten? About Witten? Yeah.
It's true. But everybody's different. So I'm often asked questions of this sort, although you've been much cleverer than most in that question. Ordering people on a straight line.
Yeah. I don't buy anyway.
One of the amazing, you meet a lot of interesting and smart, creative people, and
and I don't do a hierarchy myself. I generally don't do that.
78-dimensional space. I've discovered. So there's no order points in such a space. And anyway, the amazing thing is that everybody is so different than everybody else in so many ways, which is what makes it so wonderful.
Yeah.
All the characters in life, but especially these extraordinarily talented, creative colleagues, because they're all exceptional, but in different ways.
In different ways, yeah. And that's, by the way, that's something I tell young people too, they tend to have this stereotype of the brilliant theoretical physicist or the great scientist. And I try and say, it's not true. There's 1,000 points of light. I know people who made great discoveries who are not the best mathematically in their class, or, it takes all, when science is healthy, it takes all kinds to really make it go.
But it's not just in science, of course. It's true in everything.
In everything, exactly. Yeah.
Literature, if we had novelists were along some line,
Okay, well, let's go to the future. I mean, one of the, I know you've written about this or talked, you've had a few positions institutionally that have offered you the opportunity to, I wouldn't say pontificate, but at least to think about this as you were head of the Kavli Institute, which is an institute of theoretical physics at Santa Barbara, which part of whose job in some sense is to look at the future and try and decide where interesting areas would be for research. And then you were also president of the American Physical Society, which perhaps isn't as interesting a deal. It's more sort of it doesn't itself govern the future of physics in any real way, but it caused you at least to be to think about all the different areas of physics, probably. So how do you see is the future bright, and where do you think both in particle physics and in other areas of physics are the brightest? Where do you think are the most exciting areas? And of course, this is always,
there's many.
Yeah.
So there are really two. Well, first of all, I'm a theorist, and most of what defines the future of science is mostly defined by experiments and by experimental opportunities and technological advances that allow you to see even further. So that's true in most areas of science. It certainly was true in particle physics from its beginning. And there, I think there are unbelievable opportunities all over the place, from the instruments that now allow us to look back almost to the beginning of the universe and to study black hole mergers and collisions. I mean, to condensed matter, the structure of ordinary matter and control over the ordinary matter, including its quantum mechanical.
The quantum mechanical properties of ordinary matter. Quantum computing, are you as optimistic as some?
I'm more optimistic about quantum phenomena, including construction of quantum computers. But yeah, I mean, computing is a goal, theoretical goal. So if you develop a quantum computer, you would think that its main purpose would be to enable you to do these calculations a lot better.
Yeah.
So it'll have some impact on physics in that way. It certainly might have impact on society.
I mean, Feynman thought that it would help him understand quantum mechanics better if there was a quantum mechanical computer.
He wasn't so much interested in quantum computing, but as quantum simulation.
And,
of course. And he liked to calculate, as I do. It's nice to have these powerful instruments to simulate and calculate. But I think much more interesting for physics is the control and deeper understanding of quantum mechanics, of the quantum mechanics of systems with many degrees of freedom, like in quantum field theory or many-body theory. And that is becoming more and more powerful, possible, both with the theoretical tools, but experiment is again the driving force. There is another part of physics which I'm now more engaged in, which is more exploring the frontiers of theoretical knowledge, and that can proceed with a slower pace of experimental. Luckily, although there are dangers. I think we have such a solid base in the framework that produced the Standard Model, which is this unbelievably amazing theory, to allow us to continue in that way. Who knows what the boundaries are.
So you would say to a smart young student now that physics is a good field to go in, not biology, or I mean, not to dissuade them from biology, but it's still worth.
Absolutely.
Good.
And there are different kinds of people. You really have to find out what you really love. And physics education enables you to do some of these, approach other areas which traditionally have not been part of physics, but physics is very imperialistic, such as the physics of living matter. So physics is not a bad way to do fundamental biology.
It's becoming, there are two fields are merging in ways that I've said this before publicly, but I one of the many times I got depressed as a graduate student and wanted to quit physics, I thought of doing a joint PhD MD and doing, because they had that at MIT and my mother would have been very happy, but and doing biophysics. And I went actually to speak to the uncle of a friend of mine who was chair of cell biology at Harvard. And he said, don't do biophysics because it's not of interest to physicists and it's not of interest to biologists. And that was true back then, but it's now, it's the two, it's hard to distinguish the fields.
Well, it still is quite different. Biology is still young, exploding experimentally with new techniques and new, but their problems are deep and enormously exciting. But it's a little different. So it really depends on what you like. But there's, physics is amazing and is going to continue for a long, long time. I mean, there's a lot to be.
Yeah, oh, absolutely. Well, look, that's a good way to end. I hope that, physics is amazing. And your participation in physics has been amazing and fun to go through, and it's fun to discuss it. I hope we have a chance to discuss in 40 years from now how these things have proceeded. But it's been a pleasure, and it's been actually a really special pleasure for me because you and I know each other for many years. But what I like about this is it gave us a chance to talk about some things we haven't really ever talked about together before. So,
yeah. And the other thing for young people who are thinking, it's also fun, although very different, to build institutions and to contribute back to this incredible scientific culture and community that enables us to do science.
Yes, absolutely. And it's a fundamental part of our culture. And intellectually, some of the most interesting ideas people have ever come up with. And it's a pleasure and privilege to be able to do it. It's a privilege that we both had. And that also takes me back because I will say that I've enjoyed this conversation now. The first formal conversation the first formal, not informal conversation we ever had was the very first lecture I ever gave. I never gave a lecture as a graduate student. Was when I got into the Society of Fellows and you decided at Princeton that therefore I must have something to say, or Latin SAU, but I got invited to give a seminar. And I was terrified beyond belief because you were in the audience. And I remember at the time, there were not any really difficult questions. And I remember asking you why afterwards. You said, well, you told us this was preliminary and you invited us to ask questions, and that just disarmed us.
What did you talk about? Do you remember the title of your talk?
I think actually it was probably related to my PhD, which was on black holes in the early universe, an idea I had about black holes and phase transitions in the early universe. But it was very speculative and ill-defined. Well, it wasn't quite ill-defined, but it was enough to make me worried.
Worrying about primordial black holes.
I'm hoping that my paper, which I now understand has 10 citations based on my PhD, that'll be one of these things that in 5 years it'll become discovered. But anyway, either way, thank you, David, for the time and patience, and it's been a real pleasure.
The Origins podcast is produced by Lawrence Krauss, Nancy Dahl, John and Don Edwards, Gus and Luke Holwerda, and Rob Zepps. Audio by Thomas Amison. Web design by Redmond Media Lab. Animation by Tomahawk Visual Effects. And music by Rickolas. To see the full video of this podcast, as well as other bonus content, visit us at patreon.com/originspodcast.